$370 million gone. 4 scientific satellites destroyed. A decade of work in pieces. This is the story of how one integer killed a rocket. To understand what went wrong on that day in 1996, we have to go back almost a decade earlier. In the 1980s, Europe had a problem. The Americans had the space shuttle, the Soviets had Soyuz, and Europe had nothing. No way to put their own satellites into orbit without paying somebody else to do it. So they built the Ariane 4, and it was brilliant. Between 1988 and 2003, Ariane 4 flew 116 missions. 113 were successful. It was, by any measure, one of the most reliable rockets ever built, the workhorse of European space. But by the mid-1990s, the world had changed. Satellites were getting heavier. The market wanted more payload, more power, more capability. So the European Space Agency began work on Ariane 5. Ariane 5 wasn't just bigger, it was a generational leap. Where Ariane 4 could lift about 4.5 tons to geostationary orbit, Ariane 5 was designed to lift over 10, more than double. But here's the thing about building a brand new rocket. It costs a fortune. 10 years of development, $7 billion. And every engineer working on it knew the program could not afford to start from scratch on every component. So they made a decision that, at the time, seemed completely reasonable. The Ariane 4 software had flown 100 times. It was battle-tested, proven. So when it came time to build the most critical piece of code on the new rocket, the inertial reference system, the team chose to reuse it. That decision would destroy the rocket. Before we go any further, I need to explain something. Because the bug that killed Ariane 5 lives inside a very specific corner of how computers store numbers, and if you don't understand that corner, you can't understand why this happened. So bear with me. We're going to start simple. Imagine a car odometer, the kind in an old car, with little mechanical wheels that flip as you drive. This one has 5 digits, which means the highest number it can show is 99,999. What happens when you drive 1 more mile? The odometer doesn't warn you. It doesn't stop. It just flips back to 0 and keeps counting, as if your brand new car only had 1 mile on it. That, in a nutshell, is what computers do with numbers too. Except instead of digits, computers use bits. A bit is just a switch, on or off, 1 or 0. And when you line up 16 of these switches in a row, you can count up to a very specific number. That number is 32,767. Remember that number, 32,767. It's going to come back. Now, what happens when you try to add 1 more? It doesn't go to 32,768. It goes to negative 32,768. A positive number becomes a huge negative number instantly. Engineers call this an integer overflow, and in most software, it's an annoyance, a bug to fix on Monday morning. In a rocket, it's a death sentence. Inside Ariane 5, buried in the avionics bay, sat a small computer called the SRI, the Inertial Reference System. Its job was to know, at every millisecond, exactly where the rocket was pointed. Its angle, its velocity, its orientation in 3-dimensional space. It did this using laser gyroscopes and accelerometers. It calculated everything in extreme precision, using 64-bit floating point numbers, the highest precision format mathematics can offer. But here's where it gets interesting. The SRI didn't keep those numbers to itself. It had to send them, over a data bus, to the main flight computer, the OBC, the brain that actually steered the rocket. And the data bus, for reasons of speed and efficiency, used a much smaller format, 16 bits, signed. For small values, this works perfectly. The number fits, no problem. But the moment that 64-bit value exceeds what 16 bits can hold, the number doesn't just truncate, it corrupts. It becomes nonsense. Now, the engineers who built this knew about overflow. They weren't careless. The SRI software had 7 of these dangerous conversions, and they protected 4 of them with explicit safety checks. The other 3, they left exposed. Why? The SRI's processor had a strict performance budget. Every line of safety checking code cost CPU cycles. So the engineers analysed each variable carefully, and for 3 of them, they concluded the values would never get large enough to overflow. On Ariane 4, they were absolutely right. The problem was, they were no longer flying an Ariane 4. Now, I need to tell you about something genuinely strange. Buried inside the SRI software was a function called the alignment function. Its job was to help the rocket figure out, with extreme precision, exactly which way was up before it left the ground. You see, the Earth is rotating, the launch pad is vibrating subtly, the gyroscopes need time to settle. The alignment function watches all of this for about 50 seconds and tells the rocket, this is true vertical. This is your starting reference frame. Critical work before launch. But here's the strange part. The function was programmed to keep running for 50 seconds, even after liftoff. Why? On Ariane 4, there was an edge case. If the countdown was paused near zero for a few seconds for a final check, the alignment function needed to keep working so they could resume the launch without recalibrating everything from scratch. So the requirement was written. Keep it running for 50 seconds. Always. No matter what. That requirement was never re-examined for Ariane 5. Think about it like this. Imagine your car has a parking sensor. Beeps when you're close to obstacles. It's useful when you're parking. Now imagine somebody forgot to switch it off, and you're on the motorway at 70 miles an hour, and the sensor is still running, still calculating, still feeding numbers into your car's warning system. That's what was happening inside the SRI. The alignment function, designed for the ground, was still running in flight for 36 seconds after liftoff, still calculating a value called BH, the horizontal bias, a measure of how much the rocket was drifting horizontally relative to its starting orientation. On Ariane 4, BH stayed small, always. The trajectory was steep, vertical. Horizontal velocity built up gradually. But Ariane 5 was a different beast. Heavier payloads required a different ascent profile, a more aggressive horizontal lean much earlier in flight, roughly 5 times the horizontal velocity in those first crucial seconds. And the BH variable was one of the 3 that was left unprotected. Every millisecond, BH grew larger, and the clock was ticking. 36 seconds after liftoff. The horizontal velocity of Ariane 5 exceeds the boundary. The 64-bit BH value is converted to 16-bit, and it overflows. In the ADA code running on that processor, an exception fires. A safety mechanism. A flare in the dark saying something is wrong. But here's the thing about that exception. The engineers who wrote the specification years earlier had made a deliberate decision. Any exception, any error, the processor was to immediately shut itself down, dump diagnostic data to the data bus, and stop. Why? Because in the culture of the Ariane program, exceptions meant hardware failures, and hardware failures were random. The whole point of having a backup was, if the hardware fails, switch to the backup. It's a different piece of hardware. It won't have the same problem. But this wasn't a hardware failure. Ariane 5 had two SRIs, both running, the active one and a hot backup. Identical hardware, identical software. At 36.7 seconds after liftoff, the backup SRI hits the overflow first. It throws the exception, shuts itself down, dumps its diagnostic data to the bus. 72 milliseconds later, the active SRI, running the same code, processing the same data, hits the exact same overflow. And just like that, the rocket has no idea where it is, no idea where it's pointing, no idea which way is up. But that's not what kills it. The diagnostic dump, the debug data the SRI sent out as it died, is sitting on the data bus. And the main flight computer, the OBC, doesn't know its diagnostic data. It thinks those numbers are attitude commands. The OBC reads the corrupted bits and concludes the rocket has tilted dramatically off course. It must correct immediately. It commands the solid booster nozzles to deflect to their physical limits. The rocket twists violently sideways. The aerodynamic forces tear at the structure. The flight computer realizes something has gone catastrophically wrong. It triggers the self-destruct. 39 seconds after a perfect liftoff, Ariane 5 was gone. 4 cluster satellites, irreplaceable each one, vaporized. $370 million destroyed by a number. Within hours, the European Space Agency convened one of the most rigorous accident investigations in the history of computing. Both SRIs were recovered from the debris field. Their double EEPROM memory was readable. The investigators could see, bit for bit, exactly what had happened. Within 6 weeks, they had their answer. And what they wrote in that report should be required reading for every engineer alive today. They concluded that the operand error itself, the overflow, wasn't even the real cause. The real cause was an entire engineering philosophy. The investigators wrote that the Ariane program had operated under the opposite assumption, that software should be considered correct until proven otherwise, and that this assumption ran through everything they did. They identified 3 deep failures. The first, reused code was never revalidated against the new mission profile. The SRI software was correct for Ariane 4. Nobody re-examined whether it was correct for Ariane 5. The second, exception handling was designed for hardware failures, not software failures. Shutting down a processor makes sense when the hardware is broken. It makes no sense when the software is broken on identical units in parallel. The third, the redundancy was an illusion. 2 SRIs running identical software offer protection against random failures only. Against a systematic bug, they offer none. The aerospace industry took these lessons seriously. In the years that followed, the philosophy of dissimilar redundancy, running different software on backup systems written by different teams in different languages, became a standard for critical aerospace control systems. The certification standards for safety-critical software, D0178B, which would later become D0178C, were reinforced with the Ariane 5 case as one of the canonical examples. 16 months after the disaster, on October 30th, 1997, Ariane 5 flew again and succeeded. Over the next 26 years, Ariane 5 would fly 117 missions, becoming, like its predecessor, one of the most reliable rockets in the world. Its final flight was in July 2023, 27 years after the disaster that almost ended the program before it began. The Ariane 5 disaster is taught in computer science classrooms around the world, and usually the lesson is summarized in one sentence. A 64-bit float was cast into a 16-bit integer and it overflowed. But if that's all you take away, you've missed the point. The engineers who wrote that code weren't careless. They weren't ignorant. They were working under real constraints, making documented engineering trade-offs based on data they had every reason to trust. The code was correct. It was just running in a world it was never designed for. And that is the deepest lesson of Ariane 5. Every codebase ever written carries assumptions inside it. Assumptions about the inputs it will see. Assumptions about the hardware it runs on. Assumptions about what's running alongside it. Those assumptions are usually invisible, until the day the world changes around the code, and the code doesn't know. There are millions of lines of code running right now, in medical devices, in aircraft, in power grids, in your car, that were written for a world slightly different from the one they're operating in today. Most of the time, it doesn't matter. But sometimes, a single number, in a single function, in a single millisecond, brings everything